Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Nick from Business Review, and I will be hosting. It is our absolute pleasure to have Smith Interconnects with us today, who will be presenting their webinar titled Optical Interconnects, Addressing the Unique Challenges in Space Applications. And today's guest speakers are Arlen Martin, Guillaume Blanchette, and Benoit Reed. Now, you'll notice that our webinar platform, On24, is entirely browser-based. So if you do find any problems or disconnect for any reason, please just click on the link that you received via the email or refresh, and it should rejoin the session. In order to ask any questions at all, please feel free to send them in via the questions widget, which will be in the top right-hand side of your screen. All you will need to do is type them into the box and click submit. And if you do need any help at all, there should be a yellow help widget just alongside the bottom of your screen. And you can also move, resize, maximize any of the windows in front of you if you wanted to get a better view of the slides. And also take note of the resource widget, which you will find today's presentation along with some other PDFs and helpful content. But on my side, have a fantastic webinar, and please allow me to hand over to Arlen.
Good day. Thank you for joining us today as we discuss optical interconnects for space applications. Like space itself, optical interconnects is a vast frontier with very interesting opportunities. The Internet of Space is the last link in establishing ubiquitous connectivity to anything, anytime, anywhere. Using our phones, computers, entertainment boxes, and even our cars, we can connect to information, entertainment, and communicate easily with each other. With the rapid growth of the Internet of Things, we can control the temperature of our homes, turn on the lights before we get home, and unlock the front door. Ubiquitous connectivity to anything, anytime, anywhere. Except it's not everywhere yet. There are vast regions that do not have access to Internet or are underserved. Internet on ships and airplanes is limited or too expensive. And the explosion of the Internet of Things can put a strain on the terrestrial Internet. These problems are the last hurdles to truly ubiquitous connectivity, and they are being addressed by the Internet of Space using satellites. Optical interconnects and intra-satellite applications are used to move data inside the high-throughput communication satellites, between the switches and between the processor and the antennas. These large satellites are used in geostationary orbit to provide services in high population density regions, and inter-satellite applications. Satellites orbiting in a mesh constellation are linked together and move data around the globe. These smaller satellites are typically in low Earth orbit and can provide internet to remote and underserved areas. Guillaume, describe for us how optical interconnects are used in intrasatellite applications and what a digital transparent processor is.
Yeah, good day, everybody. Traditionally, GEO satellites have acted as simple repeaters between two antennas, as shown in the image on the left. Today, the transition to higher frequency carriers like the Ka-band enables higher bandwidth, and larger satellites are integrating multiple antennas. This increases the data throughput of the satellite, but also gives the powerful flexibility to route data between the antennas, to send the data to another beam spot on Earth, as shown on the right. These new multi-beam satellites can have several hundreds of Ka-band spot beams and data throughput in excess of 1 terabyte per second. The multi-beam satellites support higher baud rates because the Ka-band transmission frequency is higher. But this flexibility of being able to select which beam spot to use based on the data traffic requires a lot of data processing power to make that determination real time. A data processing switch directs individual information streams from one beam to another. This switch mapping can be done in real time to adapt to changing conditions in the atmosphere or shifting demand from the customer. Optimizing capacity usage in real time is a powerful feature that provides a faster return on investment for satellite operators. Onboard transparent or mesh processor offers a number of compelling advantages. By choosing the most efficient network route, transit time delays can be cut in half, thus giving an improved user experience for voice calls, video conferencing, and interactive multimedia applications. Based on customer needs, proprietary modulation and coding schemes can be implemented for secure communication links and mitigating the risk of cyber attacks or information leaks. The switchboard in the sky approach provides a satellite communication system that is not prone to disruptions or downtime due to floods, fire, terrorist attacks, or enemy bombing. It provides operational flexibility and delivers the needed capacity, coverage, connectivity, and control in support of demanding operational scenarios. There is also cost savings because less bandwidth is used for hub-to-hub transfer on the ground. This means capital and the operational expenditures are reduced for hubs, which translates to a lower cost services for users. This digital channelizer and beamformer, which provides the capability of multiple beamforming along with bandwidth routing, is not a new technology. It is similar to the technology used in mobile satellite service applications where traffic dynamics are high and the required antenna performance often exceeds the capabilities of practically deployable analog multi-beam antennas. This diagram shows the RF input and RF output data that are fed to and sent from the digital processor. Signals are digitized before being sent to the switch. This data is then switched from any input port to any output port before being converted back to an RF signal to be transmitted by an RF antenna. These high-speed switches are capable of carrying terabytes per second of data streams and require very high-speed optical interfaces. This diagram is generalization from the architecture shown on the previous slide. It shows multiple switch ports, shown in green, that are stacked together. Multiple digital optical transceivers are integrated on each of these switch ports. The yellow arrows represent the multiple fiber optical cable connections between the switchboards and from each switchboard to the RF antennas. This configuration enables a mesh network, and the use of fiber cabling significantly reduces the weight and size of such cable harnessing. The connection between the switchboard and the RF antennas are circled in red in this view. These connections exit the switch box and connect to the external RF antennas. As the antennas use RF signals, these optical transceivers are different from the digital transceivers used for the connection between the processor boards. They need to convert analog RF signals between electrical and optical for transmission over fiber cabling. This is called RF over fiber. Again, the size and weight of those solutions compared to the electrical-only copper-based solution are the reasons why these optical solutions are so attractive.
All right. Next, we will look at the inter-satellite applications. Guillaume, take us through how these satellites are actually connected to each other.
Inter-satellite links provide the high-speed connection between the numerous satellites that make up space constellations. These connections are made up of lasers capable of exchanging large quantities of data between the satellites at great speed. Link distances over 4,000 kilometers need to be bridged by equipment that must endure the extreme vibrations of rocket launch, followed by years of harsh radiation and the severe temperature conditions of outer space. The lunar laser communication demonstration demonstrated a link of 350,000 kilometers long and transmitting data at 622 megabytes per second using very compact equipment. There were two co-propagating uplinks and downlinks at two different wavelengths. While costing more than traditional RF transmission links, lasers offer much more bandwidth and are now being designed in most of the LEO constellation being deployed. On each satellite, the uplink lasers and downlink lasers use different wavelengths, shown here as the red and blue lines. There is also a third laser system on each satellite represented by the green wavelength. The satellites in constellation must keep their transmitters properly aligned to communicate with their neighbors in orbit. This is done with a pointing, acquisition, and tracking laser-based system. These lasers are at different wavelengths than the uplink laser and downlink laser wavelengths. These graphs show the filtering scheme that enables discriminating the upload from the download link as well as the acquisition laser wavelength. Dichroic filters can be used to filter out incoming from outgoing signals with more than 30 dB of isolation. A very compact 10 centimeter diameter telescope was used to create this 350,000 kilometer long link.
All right, let's take a quick survey at this point. You can respond on your screen there. Which space applications are of most interest to you? A, intra-satellite digital transport. B, intra-satellite RF over fiber. C, inter-satellite uplinks and or downlinks. D, acquisition and tracking laser systems. E, ground-based laser systems. Okay, we will close the poll and look at the results in a few seconds. All right, so the highest scoring here is the inter-satellite uplinks and or downlinks. And then we have the acquisition and tracking laser systems, followed by intra-satellite digital transport, and the ground-based laser and inter-satellite RF over fiber are tied. So a broad base of interest here of covering the whole entire system from the ground to the satellite and between satellites. All right, thank you. So let's look at the second topic of the webinar, the challenges and advantages of optical communications in space. Then let's start with the advantages of using optical connections for inter-satellite and intra-satellite links in space.
Thanks, Arlen. For inter-satellite links, because light has a shorter wavelength than RF signals, beams are usually more confined, giving a higher antenna gain. And therefore, a smaller and lighter apparatus can be used. Since light beams are more confined, meaning less divergent than RF beams, also they may overlap less to each other in space. So this helps reduce the RF pollution and lower the noise floor. In turn, more confined and less overlapping beams enable a larger number of lateral communication links between these satellites and reduces the number of base stations. When we look now at intra-satellite links, what we see is optics provide bandwidth in excess of 25 gigabit per second in lighter and smaller equipment, opening the opportunity to scale up flexible mesh network payloads to over 1 terabyte per second. And in such a dense and compact environment, a further advantage of optics is its low susceptibility to electromagnetic interference. However, optics has also its challenges, especially due to its lower maturity currently than what we can find with RF components and equipment. There are several components, like like high-density bulkhead connectors or optical amplifiers that are not yet readily available for space environments. Further, design attributes that are less important on Earth need to be reevaluated for space applications, such as adapting laser drive parameters to preserve reliability or keeping power consumption low, even at higher data rates, or even designing EDFAs with low noise figures. Sometimes even fundamental information is still often missing on very basic components, like, for example, what's the impact of radiation exposure on erbium and ytterbium dope optical amplifiers? In this picture here, we see that with RF cable, the full wiring of a satellite is a huge challenge. We are not only talking about the challenge of installing and routing all those cables and testing the installation, but also controlling the weight of all that copper, which ultimately has an impact on the cost of launching these satellites. Speaking of about the complexity and weight of copper, we see in these pictures on the top right compared to the bottom, we see the 12 fibers here, the significant drop of weight and dimension with 12 channels of optics compared to 12 channels of copper. Not only does the optical harnessing weigh less than about 10% of the copper coax solution and use less than about also 10% of the space, but fiber can also cover longer distance, about potentially 10 times longer. All right, back to you.
Okay, so we've covered the advantages of optics in intrasatellite applications. Guillaume, briefly explain the advantages of optical interconnects between satellites.
Yes. In intersatellite application, there are many thousands of optical connections between the satellites flying in a constellation. Using optics to make these connections provide numerous advantages. First, as Benoit already mentioned, the higher carrier frequency in the optical domain opens up a larger spectrum for increased capacity per link. Secondly, the optical free space links can operate at higher data rates, and this is critical for high data rate internet traffic. Finally, because optical beams are much narrower than RF beams, there is no risk of interference with other optical signals in space, and the system is more immune to jamming or interception.
And next, we will look at the third topic of this webinar, the challenging environmental conditions. In space, the temperature of a satellite can change from one extreme to another, depending if it is exposed to the sun or in the shadow of the Earth. The other significant challenge is radiation, which can damage electronics in space. Benoit, can you elaborate on the challenges these conditions pose to electronics and optical interconnects?
Yes, of course. First of all, we need to think about the impact of radiation, which is generally not a problem on Earth. On electronic components, radiation can have several effects, from the more benign perturbation of the data streams, which might be mitigated with efficient error correction, to the more severe permanent damage, which makes the component totally unusable. Obviously, in between those extremes, there's also cases of more important perturbation to the data streams, where the component may stop functioning and needs to be reset. It's not ideal, but at least there is no permanent damage. There are different types of radiation dominating at different orbits, as we see in this picture and this graph on the left. That dictates how we select the parts and also the radiation tests that we will use usually to qualify the products for such environment. Whereas commercial parts could work properly in some cases for lower LEO orbits, For higher LEO and GEO orbits, they usually fail due to the presence of high-energy protons and electrons. Choosing and testing the right parts is critical. We see here the typical environment in this table for the LEO and GEO orbits. There are very different needs, especially in terms of mission duration, meaning the reliability that the parts need to fulfill. Temperature variation also during an orbit, and the number of orbits per year inducing those temperature cycling varies between LEO and GEO, which could also have an effect on reliability. On the one hand, the mission duration for LEO are typically shorter than GEO, which could mean that a lower requirement on reliability might exist for LEO versus GEO. But on the other hand, since there is a larger number of cycling per year for LEO, which means also temperature cycling of the parts, that could also have a detrimental effect on reliability. Back to you, Arlen.
All right, thanks, Benoit. So let's do another quick survey here before the final section. What do you see as the most challenging factor about using optical interconnects in satellites? A, radiation resistance. B, reliability in space environment. C, performance specifications. D, availability of complete optical interconnect solutions. E, cost compared to traditional RF solutions. All right, close the poll here in a few seconds. And the results. So interestingly, we have a tie at the top for reliability in space and availability of complete optical interconnect solutions, end-to-end solutions. Then we have cost compared to traditional RF solutions, followed by performance specs, and finally radiation resistance. So interesting response to look at reliability and complete solutions as the most important and challenging factors of implementing optical interconnects. Thank you. All right. So finally, let's look at the main characteristics of the optical interconnects used for these applications in space. As we've discussed, size and weight are critical design factors for satellite applications. Traditional transceiver form factors, as shown on the left, are not small enough to be embedded on the circuit boards in a number of putting a number of parts on the same circuit board. Smiths offers transceivers that can transmit or receive data up to 300 gigabits per second with a footprint on the system PCB less than the size of a mini SD memory card. In addition to the midboard mounted transceivers, Smiths Interconnect has developed a blind mate optical connector that is compatible with an emerging standard in VITA, which is also being adopted by SOSA. SOSA is a consortium enabling government and industry to collaboratively develop open standards for the development of interoperable sensor systems. These optical interconnects shown here are integrated into VPX plug-in boards and the VPX backplane, and this reduces the board area required for the optical transceivers and is capable of very high bandwidth port density, up to 700 gigabits per second in one half-width backplane aperture. This solution also simplifies cable management on the VPX board. Benoit?
Yes, at Smiths Interconnect, with the Reflex Photonics brand, we have developed a platform of optical transceivers that have the perfect characteristics to be deployed in space. There's a list of these characteristics typically on the table on the left. And we have qualified these products through rigorous radiation and environmental test campaigns. We have demonstrated that these products are EMI and radiation tolerant and that they can survive the mechanical shock and vibration that happen during launches. This is a short list here of qualification tests performed on the Smiths Interconnect products for space application. The list not only includes various mechanical shock and vibration tests, but also temperature cycling in vacuum. Finally, for qualification, all these products that we sell have been exposed to several types of radiation tests while operational to monitor for any performance impact. So here is we'll talk about a more technical, for the technical audience here, a technical slide. So all the radiation tests that we perform on our products is not only done just to qualify the parts and show that they will survive space environment. With these tests, we can also extract some scientific information that is useful to calculate what could happen in the case of each customer's application. We are showing here a curve called a cross-section that we use to calculate the number of events that could happen per day at a particular orbit. An event here would be defined as the rate of bits in the data stream that's being changed in one of our tested products under radiation. The calculations from the measured cross-section show that there is about a factor of 10 difference between these rates for a GEO or orbits. For example, might be 10 to the minus 4 events per day for a GEO and 10 to the minus 3 events per day for a LEO orbit. With this, we can work with our customers for each particular application to help them meet their allowable events requirement.
All right. So today we have covered several important topics surrounding optical interconnect technology for space applications. Guillaume started with a look at the main space applications for optical interconnects for intra and inter-satellite applications. Benoit explained the unique challenges and impact of the space environment for optical interconnects and the benefits they have over traditional copper coax solutions. He also touched on the important key environmental parameters, including reliability and mission duration, temperature cycling, cold start temperature testing, and radiation-resistant operation. And finally, we looked at some highlights of the Smiths Interconnect optical transceivers for space applications. I wanted to take a moment to highlight the Smiths Interconnect website, where you can explore further our product offering for space applications, including LEO and GEO satellites, as we just discussed, and also launchers and ground system applications. You can filter down to the Reflex Photonics technology brand to see the optical transceiver series we have available now. I also wanted to highlight that it does not stop there. If you do not find a perfect match, just let us know, as we are always willing to work with you on your specific application needs. As you have seen in the presentation today, Smiths Interconnect is a leading expert in optical interconnects for space applications. Our products are used in a wide range of high reliability applications servicing the space, military, and commercial aerospace markets. In addition, we are able to offer added value services, including pre-screening of components, material traceability, and lot acceptance tests to ensure mission critical success. We are constantly pushing the boundaries of size, weight, and power without sacrificing optical performance in these demanding applications. We currently offer 3 product series shown here under our Spaceful and Space Connects platforms. The SM series are surface mounted with either direct solder attached BGA packages or pluggable parts using a mega ray connector. The SL series is attached to the PCB using an electrical interposer and screw attached to the PCB. Finally, our newest offering is the Space Connect series that we discussed a bit ago. And depending on the series and application, transceivers are available in these families at 10 gigabits per second per channel and 28 gigabit per second per channel. All are tested for radiation resistance and qualified to mil standard shock and vibration tests and operate over a recommended operating temperature range of -40 to 85 degrees C. So as you can see, Smiths Interconnect can provide a variety of standard offerings and has the design and manufacturing expertise to produce cutting-edge optical transceivers. So this will conclude our presentation for today. I would like to thank everyone for attending and participating in the presentation. I hope you were able to gather some valuable insight in the world of optical interconnects. And we hope Smiths Interconnect can be of assistance in your next application, and we look forward to working with you in the future. All right, we're looking at questions that we have here online. Let's start with the question about reliability or fit rate of your devices. Benoit, do you have some response to looking at the fit rate?
Yes, absolutely. So typically what we have been able to measure and model with our transceivers is we have a fit rate of about 20, so 20 fit per channel for each devices. So this means if some people are more used to use a mean time to failure, so that those 20 fit per channel means actually a mean time to failure more than 1,000 years.
Okay. And then while you're answering, there's a question about cooling for these transceivers. Do they require cooling?
No, the transceivers don't require cooling, except that typically how they're being mounted. So in terms of cooling, sometimes people will think about thermoelectric cooler. We don't need to have thermoelectric cooler inside the package, so they don't consume all the power that would be required for those thermoelectric cooler. But our specification is that the case temperature be maintained between -40 degrees C to 85 degrees C. So typically what our customer would do is once those transceivers are mounted to a board, there is a plate, heatsink plate that goes across the full board to maintain those case temperature within the range we mentioned earlier.
All right. Next question is, are there versions for ground-based network equipment? And the answer is yes. We have other versions, other families that are like what you see here. So we can do a lightable series, which would be an LM, which is on the left side. And in the middle, we have a LL series. So essentially, it's the same form factor, same electrical interconnection to the board using the LGA interposers, but they are not designed specifically for space applications. So they are not radiation tested and go through the other qualifications tests that Benoit talked about. So we have the same technology or the same performance in a device that is intended for terrestrial applications. So ground-based network equipment could make use of that lightable family, and also in the light connects, which would be the Vita specific product family. So yes, you will find those on our website as well.
So maybe Arden, let me jump in. So we have more.
Sure.
We have time for more questions. So if it's not obvious, the audience, we just want to remind them that in order to ask questions, you can send them in via the question widget. So just keep typing your question into the box, and we'll be gladly answering those questions, and hit submit.
All right, we have a question about the reliability or fit rate of the devices. Benoit, you take that one, please.
Yes, as we mentioned, we answer a little bit this question, so I can go back to that question. So we tend to calculate the fit rate per channel. We have in our transceivers, we have usually 4 or 12 lanes, and they operate independently. So even if a lane would go down, let's say we have a 12-channel module, even if one lane would go down, that would not necessarily affect the remaining 11 lanes. So that's why what we've decided to do in terms of fit, the way we represent that, we calculate a fit per lane or per channel, and it's typically around 20. As I mentioned, so that those fit of 20 means a fairly long mean time to failure, higher than 1,000 years.
All right. Guillaume, we have a question on the operating wavelengths of the transceivers.
Yes, so all the modules we have at the moment are parallel optical modules that emit at 850 nanometer.
Question about RF over fiber, availability. We're currently evaluating the components that we would use in that technology and gathering data and developing the product definition based on our technology platform. If you do have a project requiring optical RF, we would certainly appreciate the opportunity to discuss that, your needs, and also our timeline to the product. All right, waiting to see if there are any additional questions. If we have not responded to your question here, we will be following up with an email. All right, I think that will end the questions.
Okay, perfect. Thanks, Arlen. So, guys, thank you for, again, what was a fantastic webinar. So, thanks, Arlen, Guillaume, and Benoit. Obviously, thank you to Smiths Interconnect for sponsoring the session as well. If you didn't get your question answered, or you are popping a question in now, Arlen, Guillaume, and Benoit will be available over the next couple of days, and they will be answering it via email. So don't be afraid to ask any questions now. They will certainly get answered. Excuse me. And obviously check the resource widget as well to look at the white papers and also the PowerPoint for the webinar that will be uploaded also. And to everyone that attended, you will receive an email shortly telling you how you can access the on-demand version of this webinar. You can also access it via the Smiths Interconnect website, which is www.smithsinterconnect.com, or our own business review website, which is www.business-review-webinars.com. But on my side, we look forward to sharing all of our webinars with you. So please do remember to keep an eye on the website, or even follow us on our Twitter, which is at BR Webinars, for our daily updates.